introductory stuff today. Chapters 14 and 15. Everybody get? Top of the first page of each of these, you'll see scribbled debug. Don't mind that. I made the mistake of having these run my personal copy for each chapter. Debug means as I go through the chapter and see goofs, I'll make note of the goofs and use my debug copy to fix the goofs when I go through this the next time. Of course, as we go through this, any errors which I detect, I will remind you about it. Now, following chapter 12, gases, which we'll likely finish today, the next chapter in line is chapter 13 on solids. But to deal with solids successfully, we need a bunch of models, and I don't have enough models to give all the discussion votes for tomorrow. So I decided that tomorrow, should such be necessary, you will finish chapter 12, but then the main topic for conversation tomorrow is on the phase diagram for water. Important stuff. From a thermodynamic standpoint, a phase diagram, in this case for water, will show you how the three principal phases for a substance, gas, liquid, solid, interrelate as a function of pressure and temperature. Important. Be with us tomorrow. And regarding exam 3, prep review, I remind you again, this Sunday, I'll be here at 2 p.m. I'm sure we will be continuing the celebration of the Gators' victory of the Eastern Conference of the SEC. If you haven't noticed such, if you pay attention to this stuff. What team is the remaining team in the Eastern Conference that still has a chance to displace the Gators from being the champion of the east side of the fence? You know what it is? Which team is it? Vandy. Interesting, isn't it? They have 3 losses, but they've not yet played us. So if they win out, and that means we lose to them, and then we lose to South Carolina, they would be the East champions. I don't think that's going to happen. But we'll see how the chips fall, or how the football flies. In any case, this Sunday, I'd be glad to hold class this Friday, but I don't think I have many people in attendance. And the intended exam to be used for prep review, X3 from 45, spring 15, offers our Gower and Mitchell with the answers indicated, is now available for you, Canvas, under modules. So please attend on Sunday and bring a copy of that with you. Now, proceeding with gases and gas laws. Next consideration is that of Dalton's law of partial pressures. Dalton's law is rather important because it's commonly used in many considerations which are in regard to chemical systems that involve gases, like reactions. There are 2 parts to Dalton's law. Number one, the total pressure exerted by a system of gases is equal to the sum of the partial pressures of the component gases. So if we have a sample composed of gas A and gas B and gas C, maybe some others, but for A, B, and C, total pressure would be the partial pressure of A added to the partial pressure of B added to the partial pressure of C for a three-component system. The second part is that if there is no reaction in the gas phase mixture, each individual gas contributes to the total pressure as a function of how many moles of that gas you have. That's what this says. The partial pressure of a gas is proportional to the quantity of that gas in moles in the sample. For example, we have a mixture of gas A, gas B, gas C, and the partial pressure of gas A is moles of gas A divided by total moles times the total pressure. Now, this ratio, moles of gas A divided by total moles, is called mole fraction. In this case, it's the mole fraction of A in the sample. And this is given a symbol. Here's the symbol. You seen this symbol before? It's the Greek letter chi. Capital chi. It looks like an X, but it's got fancy wiggles on this part of the construction. It's not X, it's chi. Okay? So if we have a two-gas mixture, X and Y are the gases contained in the piston cylinder gadget at an external pressure of 1 atmosphere and 273 K STP for gases, 3 moles X, 1 mole Y. We could start by saying, would this be a rather sizable piston cylinder? If these are each ideal gases, and there's 3 moles X gas present, 1 mole Y gas present, what's the total volume? What's the volume occupied by 1 mole of an ideal gas at STP? Do you remember? 22.4 liters? Does that number ring a bell? So if we reported that information when we evaluated R, the ideal gas constant. Here you got 4 times that. 4 times 22.4. Big piston cylinder gadget. So I doubt seriously that anybody would do an experiment of this nature, but might do an experiment where, for example, you had 0.03 moles of X and 0.01 moles of Y, in which case what volume would we have? If we had 1/100th of this quantity of X and 1/100th of this quantity of Y, we'd have 1/100th of this volume, wouldn't we? So that'd be less than a liter. That would be far more reasonable. In any case, from what we said, it follows that the partial pressure for X in this sample, since its mole fraction is 3/4, 3 moles X per 4 moles total, 3/4 times the total pressure, 570 total. And partial pressure Y, 1 mole Y per 4 moles total, so 190 total. And of course, if you do arithmetic like this, you always check your work by seeing that the sum of the partial pressures is equal to the samples of the system total pressure. So let's do a couple of takeoffs on this system. What will be the value for Px and Py if into this system, with the piston free floating, we add another mole of X? Nothing fancy. If the piston is free floating, what observation will we see in looking at the piston cylinder when we add the mole of X? Will the piston remain in its original position? What will happen? piston will rise up because we now will have a system which occupies a larger volume. Because we had another mole of gas, but did not change the pressure. Kept the piston free floating. So, now the partial pressure of X is 4/5, because now we got 5 total moles. Times 760 or 608 torr, and partial pressure Y goes down to 152 torr. Partial pressure of X raised from 570 to 608. So let's play this game again, but in a somewhat different fashion. Now let's lock the piston in place. So there's our lock, whatever it is. And pump in another mole of X. Now, what will be the total pressure? Will it still be 760? Nope. What will it be? How could we determine such? Well, remember we created this condition following from this condition, didn't we? And in this condition, how many total moles of gas we got? 5. How many total moles of gas now? 6. So 6/5 times, what was the total pressure here? 760. 6/5 times 760, you ought to do it. Or you can realize that for this system, as it stands, when we go to here, we added another mole of X, right? Didn't change the quantity of Y. So what will be the partial pressure of Y? It'd be 152. We didn't change the amount of Y. We put in another mole of X. Piston locked in place. Well, in this volume, whatever it is, we can figure it out. Partial pressure Y is 152. And you're not going to change the partial pressure Y in this system at this fixed volume with constant temperature, unless you do what? You're not going to change the partial pressure of Y in this system at constant temperature, piston locked in place, unless you do what? Do what? Unless you add more Y or take some Y away. That's the only way. So, the total is now 760 torr plus 152 torr. You can do the arithmetic. The X is now six times this, what's that? 9 something. 912. And as we've already recognized, the partial pressure of Y will not change. It will remain at 152. Now then, we're on page 12:9, and we're looking at question 1228. Oops, I wrote 1228. Let's just go over here. 27. Piston cylinder, constant temperature. 2.5 liters helium gas. Helium gas is initially at 7.0 atmospheres. We're going to mix this sample of helium gas in 5.2 liters neon gas. And the neon gas is initially at a pressure of 2.5 atmospheres. And then we say we'll adjust the final pressure to 5.0 atmospheres. What's V final? Well, let's take a look at the materials we combined and the conditions under which they existed at the time in which we combined them. 2.5 liters of helium. Now the helium started at a pressure of 7.0 atmospheres. Will the helium sample experience an increase or a decrease in volume? What will it do? Increase in volume, because the final pressure exerted on the helium, since it's a part of the final system, the mixture, is 5 atmospheres. So the helium sample expands, doesn't it? Okay. So by what pressure factor do I multiply the original volume of helium so as to determine the final volume of helium? Helium is initially at 7 atmospheres and winds up at 5 atmospheres. Okay so far? You recognize that this has subjected the helium to a reduction in pressure, which means the helium will expand. Well, by what pressure factor do we cause 2.5 liters to get larger, right? Because the volume is going to get larger for helium. 7 over 5 or 5 over 7? 7 over 5, right? Now this is really tough arithmetic. 2.5 divided by 5 is 0.5, and 7 times 0.5 is 3.5 liters. That's the contribution to the final system volume by the helium gas component. Now how about our neon gas component? What the heck is this? Is our neon gas component going to experience an expansion or compression? We all agree on compression? Because the neon gas is starting out at 2.5 atmospheres, but it's going to wind up at 5 atmospheres, right? So by what pressure factor do I multiply the original 5.2 liter volume of neon? 2.5 over 5 or 5 over 2.5? Remember, the way we want to do this is by thinking about the physical behavior of the system that will be exhibited as a consequence of the changes applied. Never mind these silly formulas. that reduces this to a non-meaningful algebra stuff. So here's another real tough arithmetic question. What's 5.2 divided by 2? And I think you could add those up already, all right. No difficulty to get 6.1 liters. Good enough. And now we go to 1228. Picture. We have done this experiment in the lab. It's a good experiment. Unfortunately, we have to make a choice what experiments we're going to pursue in the lab because we don't have all that many lab dates available. Especially when this ridiculous university went to these reading days and decided to end terms on Wednesday rather than Friday. That took away a whole week of laboratory. I don't understand administration which does things like this. It makes no sense to me at all. In any case, on with consideration. Let's imagine that over here we have a reaction flask. In the reaction flask, I'm going to put 6 molar hydrochloric acid solution. What is in the 6 molar hydrochloric acid solution? Hydronium ions, chloride ions, water. Bingo. Into this 6 molar hydrochloric acid solution, I'm going to add a weight sample of zinc metal. Because zinc, like many metals, will react vigorously with hydronium ion and liberate hydrogen. Have you had any experience with this reaction? Have you had any experience with zinc reacting with hydronium ion, this term in lab? Yes or no? Assignment 5, Part 1? Or is that already buried in the archives of ancient history? I mean, that's at least a few weeks ago, so cobwebs have already fogged over your memory of that. You know, I'm laughing like you relate to each other as much as possible. A redox reaction. We need to write the equation for the redox reaction for this consideration. But in order to do this, what we'll do is to stopper the flask, drill a hole in the flask, put a piece of glass tubing, in the flask, and have the hydrogen gas that's produced by this reaction travel through this curved tube, which is inserted into the bottom of this inverted graduated cylinder. And so, as the reaction proceeds, water is going to be displaced by the entrance of hydrogen gas into our inverted cylinder. So let's imagine that the piece of zinc which I reacted completely caused the generation of this much hydrogen. Is hydrogen particularly soluble in water? What do you think about that? We really haven't talked about this specifically, but you ought to have a good idea. Because we've laid foundation for your understanding this. Is hydrogen particularly soluble in water? Why not? Hydrogen is the simplest possible non-polar molecule, whereas water is a particularly electric material, isn't it? Not only has it got a large dipole moment, because of its angular nature and composition, it also is a hydrogen bonder. Upshot of which is that water molecules would much prefer to stick to each other than they would to hydrogen molecules. So this is an effective way to collect hydrogen without having to worry about hydrogen being dissolved in the water. There will be some, but it's minuscule. With Henry's law, we can figure out how much hydrogen is dissolved in the water. Never mind Henry's law for now. We'll talk further about that when we get to solutions. At which time we will recognize that in an experiment of this nature, the amount of hydrogen which would dissolve in the water during this reaction would be negligible. Now the next question is the hydrogen gas we collect by this method pure hydrogen gas? Or is the hydrogen gas, and remember we started with a cylinder completely full of water. Or is the hydrogen gas mixed with another gas? If so, what's the other gas? Water vapor, you betcha. Question then. If I want to find out how much hydrogen gas I've collected, how do I adjust for the presence of the water vapor that is also in the sample? What property of water must I consider to make this adjustment? It's called what? Called vapor pressure for water liquid. What's vapor pressure? If I tell you the vapor pressure of a liquid or a solid, what have I told you about that liquid or solid? I've told you about its tendency to convert to vapor phase at the temperature of the sample. That's what I've told you. Vapor pressure in some is a measure of tendency to evaporate at sample temperature. In the notes, do you see a vapor pressure table for water liquid? Now, I suggested that this experiment be conducted at 26 centigrade. Tell me, by looking at the data that you see before you on page 12 now, give me a gee whiz estimate of the vapor pressure of water liquid at 26 centigrade. What say you? Notice that at 25 centigrade, the vapor pressure is 23.8, and at 30 centigrade, the vapor pressure is 31.8. So as I go from 25 to 30, temperature-wise, the difference in pressure is greater than 5, isn't it? 5 total. Do you think it will be the case that for every 5-degree increase in temperature, the pressure will also increase by the same amount? Look at the information in the table. As temperature gets higher and higher, what happens to the corresponding vapor pressure? It gets quicker, faster, doesn't it? Okay? So give me a gee whiz vapor pressure for water liquid at 26 centigrade. Don't be bashful. Yuck! Tell me what you think. 25. I'll take that. 25 total. Now then. What arithmetic should we do? To find out collect if, pardon me, how much hydrogen we would have collected. If we're able to capture this sample, which we have reported to exhibit a volume of 728 mLs, and I'm going to put down wet H2 gas, wet with water vapor. What will the volume be if I have a way to seal this off so I can stop evaporation of water, liquid to water vapor into the sample, and go in here and pull out the water vapor? How will I find this volume? What did Dalton's law just tell us? We have a two-component gas system, don't we? Hydrogen gas, pardon me, and water vapor. And we've found that the vapor pressure for water liquid at the temperature 26 centigrade, which is the temperature under which we ran this experiment, is 25 torr. What's the total pressure acting on the system? Look at the question. Pressure total is 772 torr, isn't it? And this is equal to the sum of the partial pressures of the components, isn't it? Have we not recognized what the partial pressure is of one of the components? What is that partial pressure? 25 torr. So, if I'm able to go in here and remove the water vapor, will the resultant hydrogen volume be the same, smaller, or larger than 728 mL? Smaller. I'm going to pull out the water vapor, right? Oh. Will this do it? This does it. Now, let's ask one more question about this sample. What if I wanted to know how many moles of hydrogen had been collected? What would you do? Volume over 22 points? Well, what do we know about this volume? What's special about this volume?
STP.
What's special about this volume?
STP.
It is the volume that will be occupied by 1 mole of an ideal gas at STP. Good. You think hydrogen will behave ideally? You betcha. As far as interparticle attraction forces are concerned, practically zilch in hydrogen. Go ahead.
Isn't it at 26 degrees though?
Well, we didn't do the arithmetic yet. All we said said so far is the physical significance of this number is this the volume occupied by 1 mole of an ideal gas at SDP. Okay? Now I want moles. So I'm going to write 1 mole, in this case it's H2, and 22.4 liters. Have I got 22.4 liters? Well, I got this volume, don't I? Okay? It's the volume of hydrogen that I already have collected under these conditions. That's if I did the arithmetic someplace. Yeah, this one gives 704 mLs dry H2. So I'm going to write 0.704 liters H2. Okay? Now tell me, I collected my hydrogen at 26 centigrade and 772 torr. My 22.4 liter data point corresponds to 0 centigrade and 760 torr. Okay? So if I'm going to imagine taking this sample of hydrogen at a volume of 704 mLs and converting it to SDP as a function of temperature change, will hydrogen volume increase or decrease? I collected the hydrogen at 26 centigrade. That's 299 Kelvin. But the 22.4 liter data point corresponds to 273 Kelvin, doesn't it? So if I'm going to imagine converting this hydrogen from 299 Kelvin to 273 Kelvin, is the hydrogen going to expand or contract? Contract, because I'm cooling it. Oh. Now then, I collected this hydrogen at a total pressure of 772 torr. But I am now considering its volume at what pressure? 760 torr. So as a consequence of this pressure differential, will my hydrogen sample expand or contract? Expand, won't it? So my pressure factor is and I say again, this is the way to do this stuff. Never mind these formulas. If you think about the physical changes applied to the sample and recognize whether or not by the temperature change it experienced, does it expand or contract? By the pressure change it experienced, does it expand or contract? By moles added or subtracted, does it expand or contract? You'll always get this right. But if you're looking for some formulas to shove this in, not the way to do it. You can grind out the arithmetic. Now then, one last consideration. Page 1210. How many of you have heard about relative humidity? Everybody's heard about relative humidity, haven't you? How many of you know what it means? I got one hand. Only one person in the audience knows what relative humidity means. Well, on page 1210, you will see that relative humidity is expressed as a percentage. Otherwise, it would be a decimal fraction. action as a consequence of comparing the actual quantity of water vapor in the air. The actual quantity of water vapor in the air relative to the capacity of air at that temperature to keep water in the air, water in the vapor phase. Okay? And if the actual quantity of water in the air, water vapor in the air, pardon me, actual quantity of water vapor in the air is equal to the total capacity of air to support water in the vapor phase at that temperature, what kind of relative humidity do we have? 100%! Beautiful. Now then, I have here a very, very special device called a thermometer. And if I had my way, you'd still be using these things in the laboratory, so you know how to read things. Not just automatic electronic stuff. That teaches you nothing. The administration insists on we modernize. That's interesting when we modernize and at the same time throw away learning. I don't get that. I don't accept that. You can see how much they listen to me. Now notice what I've done with my thermometer. I have wrapped around the business end, perhaps you can recognize that, a piece of Kimberly, and I've secured it with a little bit of Scotch tape. Okay? Have you ever heard of whirling psychrometer? Whirling psychrometer is the fancy name for the gizmo that the meteorologist uses, the weather person, to measure relative humidity. Well, I can measure relative humidity in this room right now with my gadget just as well as they can do it with this fancy device called a whirling psychrometer. Okay? Now, it's kind of warm in here. And I'm looking at a temperature for this room right now. Write this down. 22.8 centigrade. That's what I got. 22.8 centigrade. Write that down. Everyone have that down? 22.8 centigrade. Tea room. 22.8 centigrade. I guess that's not too bad. Just that I jump around a little bit. Now, I got some water in my cup. Take it from here. Good stuff. I'm going to wet my kidney. Now, I've wetted my kid wipe. And now I'm not applying to you a blessing. I know about salvation, I do not know about salvation. Tell me, as I do this, what is happening to the water liquid that I just applied to the Kim wipe at the business end of my thermometer? It is doing what? Evaporating. And I'm doing this rapidly. See, with a whirling psychrometer, with the weather person then whips it around us, so the evaporation rate is quite fast. Now, as a consequence of evaporating, because I need to consume heat to evaporate, since my wet Kim wipe is in immediate contact with the business end of my thermometer bulb, it's taking heat from the thermometer bulb. That causes, in here, the mercury column to shrink, and the temperature's going down. Okay? Now, I wish to continue with this action until I observe what kind of temperature reading on my thermometer. It'll get lower, but I want that temperature reading to become constant. Because when it's constant, what condition has been established here at my wet Kim wipe wrapped around the thermometer bulb? 100% relative humidity. Aha, right? And then the temperature will be constant because the rate of evaporation of water liquid at the business end of my thermometer will be exactly equal to what? The rate of water vapor condensation from the air back onto the wet Kim wipe. I will have water liquid, water vapor equilibrium established. That's my Kim wipe wrapped around the thermometer bulb. Good exercise. Oh my! Let's see what we got now. 6.8. Well, in any case, you see how the game is played. Now, I will ask you a question, and we'll finish this question when we see each other next time tonight. Well, I won't do this on Sunday. We live on Monday, okay? I'm going to ask you that if the relative humidity in this room is 70%, I'm just making a guess, it's probably about 68%. If the relative humidity in this room is 70%, what will be the equilibrium temperature that I am going to observe? You determine that. And if you determine that, you'll know how to deal with the relative humidity. Okay?